We are ready to go. The floor is yours.
So we'll be talking about a project that's been 3 years in the making, and we're in the final stages of wrapping it up in the next few months. So we're really excited to be able to share it with a bigger community and get your feedback and that sort of thing. So I'm Marinia Kolak. I'm a health geographer, but I took kind of a tangential path to spatial epidemiology and what we're calling spatial data science. I actually have a John Hopkins connection. I got my master's in GIS at John Hopkins, so go that. um, and I think a lot of the work that we're doing in this project that is not afraid of working with many different types of data, including really complex satellite data, came from my time learned at John Hopkins. So that's super exciting. And then Isaac, did you want to just quickly kind of give a quick intro of what you, who you are, what you're studying, and that sort of thing?
Hi, I'm Isaac. I'm a fourth-year undergrad at the University of Chicago, studying geographical sciences, and I've been on Marinia's air quality team for a little over 2.5 years now. And yeah, super looking forward to presenting this with her.
Yes, and I was lucky to grab Isaac early in his undergrad career. So he's kind of an unofficial grad student in our group for the most part. But, all right, great. So we'll be talking about this. Next slide. So first, the challenge that kind of was posed to us. So this is a project that is connected to both our stakeholders are essentially policymakers or different thought leaders within the Chicago Public or Department of Public Health. And this is a project that from a wider perspective is funded through Bloomberg Philanthropies. And the challenge posed to us comes from essentially, so within the literature, there's been numerous studies that have found concrete links between fine particulate matter. We spent a lot of time talking about PM 2.5 microns, but it can go up to, so PM 10, there's also a lot of connections with that and adverse health outcomes as well. So while we know this, this to be true, and there's many different articles out there, documenting this connection, what does that actually mean? How can we kind of integrate that into a more thoughtful way so that that data and all the different factors driving those outcomes can be shared with communities, decision makers, and so on and so forth. How can we extract small area estimates of air pollution to support decision making? And there's a lot of different associated challenges. So how do we actually define and measure air quality? It's not a straightforward path by any means, and we make a lot of decisions in this approach to simplify and potentially oversimplify, but it's a complex topic. What about the factors that drive or impact air quality? So on the one hand, we have measurements of air quality, but then on the other hand, being able to see what are potential drivers of that in the same setting could be really interesting. Next, what about changes over time? So while we're kind of coming from a geographic perspective, things like air quality really exist on a temporal scale, right? So in the landscape of COVID, for example, looking at COVID cases from 4 months ago might be interesting, but it's such a temporally driven concept, right? So air quality that is also the case, and then you add in the complexity of seasonal variations, climatic variations, and so on and so forth. And then finally, what tech is available to process and present the data within our needs? So from my background, I come with a lot, I've done a lot of work with different community organizations, different scales of public sectors, and oftentimes what's considered the gold standard may not be available to groups because of cost, right? So the cost of the software itself, and so on and so forth. So in our case, we had a little bit of funding through the grant mechanism, but our goal was essentially how can we develop a system that can be passed on to city stakeholders in the long term that would still make sense, right? So if we create a really elaborate, you know, very complex system in one language, and then no one at the organization that we're passing it on to uses that language, it's not very meaningful, right? So what about how can we use tech in a way that's sustainable? And R ended up being the answer for a lot of these questions. So next slide. All right, so a little bit of a background of kind of zooming into our focus on how can we make air quality metrics accessible within a dashboard. So dashboards are often used to inform researchers, the public, policymakers at different stages. Um, there's a really important kind of balance that occurs where you need to balance opening the information and raising awareness, but then also provide sufficient context, right? So we don't want to just throw out all the data that exists and see what sticks, because information is complex, right? There's a science to kind of processing what can be communicated, how much uncertainty is appropriate, how much is too much, um, how can data be um, construed and misconstrued in different contexts. As you can imagine, this is a big problem with the COVID pandemic as well. Um, but from our side, dashboards often disregard trends in favor of showing snapshots of a current situation, whereas our project has a really strong temporal dimension. So we're essentially going to be taking data at a 1 kilometer resolution across 21 counties in the Chicagoland area. And our goal is to provide that information whenever possible at a monthly resolution across 5 years, from 2014 to the end of 2018. So quite a challenge faced ahead of us. So one of the results of this has been the Open Air Chicago dashboard. And again, as I alluded to earlier, this is part of a larger project where we're trying to examine local trends in air quality in and around Chicago. The goals of the dashboard are to provide a free open source means of visualizing and analyzing air quality data. And here the term analysis, analytics, will have multiple meanings, but I really want to emphasize the visual analytics that occur when we are working with dashboard interfaces. So for those informaticians out there, you know what I'm talking about. There's many different ways to visualize data. So our goal is, how can we present data in the most authentic way that retains the most information? And then another piece of this is how can we improve access to air quality information for policymakers and the public. Right now, there are dozens of reports and places where you can get air quality information. So our goal is not to replace all of those individual ones, but rather curate, integrate the core pieces of that into kind of a customized framework that can be useful. So this project, while the research component is led by our team at the Center for Spatial Data Science, we are working with close partnership with the Chicago Department of Public Health, specifically their innovations team. And the goal is to how can we use this information to support, inform policy decisions and affect citywide change as part of the Bloomberg's Partnership for Healthy Cities. I do want to caution at this early stage that this is really not about um, uh, monitoring air quality for surveil or for enforcement. That's a different direction. That this dashboard is really meant more to serve as an exploratory tool in a less kind of legal and restricted environment. Okay, so what is the data? We are working with a lot of different data sets. The first suite of data sets will be what are the actual measurements of PM 2.5. So we really focus on 2.5. ISAC will later show a few other measurements that we have as well, but because of turns out data limitation issues, we felt that PM 2.5 had sufficient data to make analysis a little bit more meaningful. So we get PM 2.5 from multiple places. And this actually ends up exploding into another project, which will be another talk. But we use ground-based sensors. And the highest quality ones that we have found that work consistently, even though there can be errors sometimes, but over time they provide the highest quality measurements, are tax-funded EPA sensors. So these EPA sensors provide high quality measurements that are documented in the literature over time. Unfortunately, the sampling is not spatially random. So there will be challenges based on where the sensors are located throughout our study area. And there are only relatively few points throughout this. So there's different ways to deal with this. We'll touch on some of them. One option is to interpolate the surfaces, and that essentially is we're inferring air quality measurements between EPA sensor points. So this is really an issue of missing spatial data. So you can infer the values in between points using many, many different spatial point pattern analysis techniques. Unfortunately, the results will vary dramatically based on the method used. So while, so AQI, many of you are probably familiar with that, that is essentially taking air quality measurements of PM 2.5 and I believe ozone. That will use an IDW method, which is one of these interpolation methods. This is just something that exists as a limitation. There are alternate ground-based sensors that are kind of considered like lesser quality, but more affordable. So in the Chicagoland area, the big thing here for quite some time was the Array of Things network, which were lower cost network air quality sensors placed throughout the city. Unfortunately, we found being early kind of explorers of this data that over time, because of the lack of calibration and a number of other issues, the sensors did degrade over time in a noticeable way. So we're noting that this may not be as, they're just not going to compare to the EPA sensors. But another way to measure air quality is by satellite-based sensors. And this is not a direct measurement, but rather an indirect measurement of air quality. So we'll spend a lot of time using Aerosol optical depth. That's a satellite product that has a multivariate correlation with particulate matter, including multiple other variables like elevation, boundary layer, so on and so forth. This does require a much more sophisticated model that we will include, but it ends up being another factor. The nice thing about aerosol optical depth is it covers the majority of the location. So instead of just having a few sensors and a couple points scattered throughout your study area, now you have almost full spatial coverage at regular temporal resolution. So it's updating on a regular basis. There are challenges with this as well. So you will get more missing data on cloudy days, which is something that provides challenges. But we end up using the 1 kilometer resolution of aerosol optical depth, which is actually, it is derived using something called the MAIC algorithm. But there has been quite a bit of, we're essentially, our goal is not to create any new methods here, but just replicate existing methods of how to integrate ground-based and satellite-based sensors. Okay, so next up. There's also a lot of different other air quality drivers. And from our perspective and from kind of the wider perspective, this was even more interesting, right? So there's many different things that impact air quality from, temperature, precipitation, wind, but then also vegetation, land cover, land use from a zoning perspective. We're also interested in grabbing area emissions like road and traffic estimates, and then point emissions. And these are factories and or facilities that have permits to release PM 2.5 in different ways. So that comes from the National Emissions Inventory. Also things like albedo, which is going to be related to, especially when we pull an AOD elevation. So our goal was not to just do one model, spit out the output and pass it over as a report, but instead create in this interim stage, how can we visually show, provide a place to integrate all this data and visualize it for meaningful exploration and that sort of thing. So next slide. So just another kind of view of the data. So this ends up being 17 variables. We integrate all of the data, and this is the tricky part. So the data is integrated using R, using different geocomputation methods to basically reshape the data so that it fits the same 1 kilometer resolution of grid cells across our 21 county area. So our scale of analysis is a 1 kilometer grid cell. We use both vector data, so some of the data like road lengths are in lines, so that's called a vector data format, whereas other data like the vegetation index will be a raster, and a raster is essentially like if you're looking at a satellite image of Chicago or Baltimore, right? It's a pixelated data set, so we can get vegetation as a pixelated representation our goal is, how do we take points, lines, polygons, pixels, and recompute all of that at 1 kilometer resolution grid. This is a huge data processing feat, and we did that in R. Well, I should say ISAC, who's now become our kind of lead senior RA, ended up doing a lot of that. So, and again, so the goal is to provide all the data and dashboards, and then make the downloadable, or make those final outputs easily downloadable. So it's essentially, there's a massive standardization process happening here. And this is seen as easier for really busy, public sector workers or community organizations who just wouldn't have the time or the like bandwidth, or in some cases, some of the expertise to do all of this one by one. So next slide. And so in order to do this, there are multiple workflows that are generated for each variable. And one of the additional kind of extensions of this is documenting what those workflows are, both as diagrams in some cases, but otherwise using R Markdown. And then finally, another product that we're working on is developing an open air quality toolkit that basically guides users through the whole process of how we extracted the data, transformed it, and then pushed it out into the format that we need. So I think the next slide has a really nice diagram that ISAC had created. So for example, in this case, grabbing OSM Metro extract data, and OSM stands for Openstreetmap. So in this case, grab all the road networks from Openstreetmap, which is a free open source, but then also grab the 1 kilometer grid shapefile that we want to, transfer the data to. And then there's multiple different steps along this process before we finally write to the a clean data format. And I should note here that that whole process, that was really drilled into me during my master's experience at Johns Hopkins. So I feel like there's a definite Baltimore stamp on this. All right, so next step. And then what do we use for this? Spatial analysis in R really requires, for modern kind of context, we really need the SF package. This is in contrast to SP, which is, I think the early version of some of this work was done in SP, but it tends to be slower. It can be very good for some types of point pattern analysis that work on these old, different systems, but today, SF, it stands for simple features. If any of you are SQL nerds, like myself, this is kind of our extension to PostGIS. So PostGIS uses simple features. It's basically a international standard for working with spatial data, and it provides a lot of different ways to read different data sets. So that can include shapefiles, GeoJSONs, and then also the different kinds of raster data sets that you have to work with when it's added, or loaded up with additional package connections, but then also things like spatial joins and intersections. So a lot of the data standardization is, how do these roads match up over the 1 kilometer grid? So spatial joins and intersections are going to be the heart of a lot of that. Cool. So next step, and then for spatial interpolation methods. I know that you guys want to get to the R shiny stuff, so I'll try to go a little bit faster here. But again, this is using known values at points to, instead of having just a couple points there in an area, you create a surface. It's kind of like a predicted map of what values of different PM 2.5 sensors readings would be. There's a lot of different methods, from using Thiessen polygons to inverse distance weighting to kriging. These are varying degrees of sophistication from a geostatistical perspective. We can come back to this if there's questions, but a lot of the data, so we didn't want to just provide points. We also wanted to provide surfaces. However, because some methods are better than others, we kind of, and the latest iterations may flip to better models. So what do I mean by that? Rather than have an interpolated map of PM 2.5 sensor readings, we ended up doing a neural net model that incorporates aerosol optical depth and a lot of other things, and now bring in that output into the dashboard. So that's a very quick way of explaining that. So next slide. And then if you are interested in IDW, and I should note that even for those more complex models, like the neural net model, a lot of the data as an input needed to be shifted into an IDW format to make more meaningful input values for models. So I don't want to bash interpolations at all. It ends up having different uses in different cases. If you're interested in working with spatial interpolation work, look at the GStat package, the SpatStat package. I would also Google point pattern analyses R for a lot of different kind of toolkits that go around there. So here's a formula for the IDW perspective. And again, the goal here is we have points and we're trying to, switch the points to a continuous surface through the region to make things more interpretable. All right, so next up, so vector data, just to kind of emphasize, I've used that word a couple times. Vector data will be imported into R from shapefiles, and then often we'll have CSV values that will get merged to that. So you might have vector data of a road network. You might have a CSV of different facilities and their PM 2.5 emissions values, or what they report emitting. And we then have to read that in as a CSV, geocode it, convert that latitude and longitude into a spatial point, which is a different format than a CSV, and go from there. So there's a lot of complexity to this. But again, it's so I'll leave that question for Isaac so that all right, so then balancing information. Okay, yeah, so I'll leave that for there. So for raster data, oh, go ahead.
There was a question in the chat. Do you prefer them at the end or do you prefer them as you go along?
Yeah, I think that, yeah, if you want to ask that now, because I think that.
Sure.
I saw something pop up.
There's me encouraging everybody to post questions, and then a question from Mike saying, is there an option in multiple imputes for a spatial data?
And so multiple imputes, because do you mean?
There's like the mice package, something like similar. I mean, there's methods of multiple imputes where there's different ways. This is just another one of a wide variety of ways to fill in missing cells. But I wasn't sure if there was an option there for spatial data, or have you considered that?
That's a really great question. I think that the kind of standard, because there's so many different steps of checking it. So I think the standard now is run different types of, and actually when Isaac goes, I'll put a link to one of the toolkits that he developed that kind of goes through this. But a different way would be like you run different types of interpolation models, and then you compare the results using both the figures, but then also the maps to see how things shift. So it's more of an informal way of doing it. It doesn't, yeah, that's a good question. I don't think I've seen a package that forces kind of all of them at once, but it might be because the outputs get kind of complicated. Isaac, do you have anything to say about that?
No, that covers it, yeah.
Okay, now that's a really interesting question. That might be a future R package suite that that could be put together. So we'll have to follow up with you and work on that. Okay, and so then for raster data, so rasters in this case are going to be typically imported as GeoTIFF files. I'd say that this was probably the biggest challenge when we first started on this, where I was initially like very much neutral to what language we use. Like it doesn't matter if it's Python or R, etc. Like what method makes the most sense. It was interesting that there were a lot of different conflicting toolkits out there available at different agencies and groups, where I think there was like the whole debacle between HDF4 and HDF5, and how do we, integrate all this together. But again, we ended up using R as the final version. But again, similar integration challenges, but the purpose is always to reaggregate rasters both spatially and temporally. So there was that kind of added challenge. And next up, I think that, and then the neural net model. I won't spend too much time here because this model was, I think that Hawen used Python actually, so I don't want to say that too loudly in an R group. So, but separately, all the data that was processed ended up going out, and this is a nice part where you can start to communicate between different languages. So that all that data was and processing produced a cleaned data set that had huge spatial and temporal variability that could get piped into a neural net. And the output of that neural net we found to be even more effective than the interpolated PM2.5. So that's why it's included here. And here's just one snapshot from August. It seems like August overall has consistently like the highest peaks of PM2.5 in the Chicago area. And another kind of big trend is that we found that there was things generally improved between 2015 and 2018, and then it started to increase in 2018 again. Okay, so I know that I think the next slide is switching over to ISAC. Is that right? Okay. Well, and I talked a little bit about this of the different data formats already. And I think too, so like for our group, like we had, we're really used to coding for a long time, really used to spatial data, even though I had been trained in some kind of satellite-based raster analysis years ago. This was just a much bigger scaled challenge. So, so really highlighting how, even in very well documented different fields, like translation between subspecialties is a challenge. So our goal through this project was to kind of, again, both provide a place to communicate the data with the inputs and the outputs, but then also how can we, package this in a way that others don't have to struggle as much as we did. So that being said, yeah, I think that, or ISAC, do you want to switch over here? This might be a good place. Yeah, perfect.
For sure, yeah. So so now gonna jump right into the dashboard itself. So you're gonna start with kind of like the process of like iterating the dashboard and then going into the more specifics, like the R packages that were used, how they were used, and so on. Yeah, so in the early stages, we weren't really sure what form this was going to take. We had known that we wanted to do something with localized PM2.5 trends, but we were kind of agnostic as to how we did that. So Marinia touched a little bit on this earlier, but we kind of started out with doing some work in Python, some work in R, and we eventually settled on R because we thought it gave us the best platform for processing spatial data. And also because R-Shiny kind of presented itself as a flexible way to develop and distribute this dashboard that we wanted to make. So prior to having this dashboard, we worked through kind of existing platforms with the city. So they have a Health Atlas where we published some of our process data, but this platform working within like the R-Shiny framework gave us some options for developing that more. And these early stages, not going to go too much into this again. We were focused pretty heavily on the array of things sensor network. But because of questions over that, we kind of found a need to transition into presenting kind of established data sources in a way that is more easily accessible than before. And so that leads us to the dashboard. And this was kind of our stage 1 dashboard, where we provided different variables of interest for air quality. So the different drivers of air quality that we've discussed, each of them will have like an individual variable page. Each of these pages has an interactive map, a brief description, and this initial dashboard had a pretty heavy focus on the city of Chicago itself. So you can see on the top that we have like the different community areas, which is the neighborhood level breakdown in the city, and kind of the readings of given EPA sensed value over time in a given community area. But unfortunately, this initial dashboard ran into some issues. It took quite a bit of time to run. It had like a 90-second runtime, which made it pretty limited use for the kind of policy implementation that we had hoped. And it also, it was pretty hard to iterate with because it made extensive use of CSS, of JavaScript. And so we kind of found ourselves wanting to kind of reiterate it as a more clean and more kind of streamlined environment, which leads us to the stage 2 dashboard, which is kind of what I'll be talking about and where we're at now. So this is our stage 2 dashboard, and I'll have a live demo in a few slides. But kind of the TLDR of the areas of improvement with this are shortened runtime. So whereas before there were a bunch of different data inputs, reading in probably a few dozen files, all the data here is compressed into, I think, 2 files for substantive data. So we have like a single raster file with different layers for each of the variables, and then a single vector file with different points representing sensor locations, and then a CSV or 2 with averages. And then we also wanted to upgrade the overall design and streamline the R scripts to make it a lot easier to iterate. And kind of most importantly, we wanted more options to compare across different variables, because a kind of pitfall that we've seen with earlier dashboards and also that we sort of fell into with our stage one is that we had a lot of options for looking at variable changes over time, but we weren't really sure how we wanted to go about comparing like different variables and how they changed over time. And so I'll get into how we did that later on. So this kind of process of iteration was very much driven by the relationship we had with Chicago Public Health. So specifically the newer dashboard, we've expanded our focus from the city of Chicago to this expanded area of 21 counties. And that was very much a factor of the city being interested in how outside areas influence air quality within the city. Because obviously air quality is not going to be something that's driven entirely by processes within the city, even if it is air quality within the city. So it was important for us to consider surrounding areas, surrounding counties, and see how these might affect Chicago. We also kind of worked with them on which variables to include, on the visualization options that were kind of most intuitive and most informative. And so here's how that looked. So when building the dashboard, obviously used a bunch of different R packages. Here are some of the most important ones. So broadly speaking, we worked in the framework of our Shiny and like a Shiny dashboard, which are kind of the two base packages for building up this sort of environment. We used, so Shiny comes built in with some widgets to interact with, but there are additional widgets in the Shiny widgets package. There's a super great package that I'll talk about next slide called Dashboard Themes, which allows you to kind of move beyond the base level Shiny appearance into a really customizable end product. And then the interactive plots and graphs and maps were done with Leaflet and Plotly. And then our spatial data analysis were done with the SF package, which Marina talks about, and also the Raster package for Raster Data. So on the front end, here's kind of the progression of our initial dashboard on the top to where we are now on the bottom. And so those kind of, if you've worked at all with our Shiny before, you probably recognize the theme for the top dashboard as sort of the base level our Shiny theme that you get with everything. And so with the dashboard themes package, this was like a super exciting change because you're able to kind of move beyond that and customize things. So we were able to kind of make it more Chicago with the colors and the layout. And so that package allows you to change like the color set for everything from buttons to sidebars to the different gradients. And so all you need to do is just input in like a color value into the different parameters. There's like probably over 100 different options there. And you can change pretty much every element of a Shiny app with that package. Additionally, on the front end, through different widgets, you're able to cycle through a couple of map views. So whereas before you were restricted to looking at the city of Chicago, now you can look at this expanded 21 county area. And also when visualizing this data, we wanted it to be possible to view both trends like within a single snapshot of time. So we wanted to have a color palette that drew distinctions between hot spots and cold spots in a given, like a single picture, like a single month of readings, but also see that in reference to overall. So you have changeable color palettes based on whether you're trying to identify like trends at a given time or trends over a longer period. And so when you're building an R Shiny app, kind of your main point of interaction are going to be through widgets. So these are going to be your buttons, your sliders, your different boxes that allow you to engage with the app itself and change different things. So I'll go through kind of how we implemented a few of these and how they can be implemented more broadly. So on top, you can see like an example of a slider input. So you can use these for date and time sliders, which is how we use them, where you can customize the different tick boxes and you return a date or a like integer, depending on how you have it set up. And with that, you can then filter your data, subset your data, and show only the data for that period. Then you have like a selectize input where you can select multiple variables, select one variable, and it will return the variable names in a vector that you can then use for filtering. And then finally, like a radio button, you can just have it where it'll be observing an event with one of the dynamic functions in R Shiny, and it will then change your kind of view, your palette, whatever you have that button set to based on whether, like when that button is clicked. So probably one of the most important packages that you can use if you want to visualize spatial data, both in R Shiny and beyond, is the Leaflet package. So this allows you to create interactive maps in a way that works seamlessly with the RShiny environment. So there are a bunch of packages that do interactive maps. Leaflet is probably the best for RShiny because of how it works with inputs and rendering and like dynamic changes in response to like user inputs. So when you're building a leaflet structure, a leaflet like object, you kind of pipe in these different layers into the main leaflet function. So you have like provider tiles, which are essentially your base map. So for the map on the right, the base map would be an OpenStreetMap one that comes preloaded, but there are dozens of different options. Then for the one on the right, you'd add the raster image, which would just be that kind of green, like the reflection of how much green space there is in each tile. Then you'd add like the polygons, which is that shapefile showing the different counties. And then finally the legend. And Leaflet, kind of one of the reasons it's super great for RShiny is it gives you a lot of options for customizing how it zooms, how the color palettes work, and a lot of other things that really lend themselves well to a bunch of different maps, like rendering a bunch of different maps and kind of manipulating these maps for the end user in a way that's really intuitive. And another great advantage of Leaflet is it works really well with some other interactive packages that you can use in Shiny. So here's an example of using Leaflet with a package called Plotly, which kind of generates interactive graphs if you've been exposed to it at all. And you can have the two kind of dynamically change with one another and create a cool way of visualizing something both like spatially and like just over time. So it's a really cool way of integrating two different types of data and types of data visualization. So in this case, clicking a polygon, in this case a county, on the leaflet map will return that county's ID value, which you can then use to filter the CSV that you're using to generate the time series plot on the right in the Plotly plot. And so both of these packages are really conducive to dynamic rendering, which you can do in RShiny with a bunch of different functions. In this case, we used observe event, which kind of just waits for a click to happen on the map. And when that click happens, it re-inputs the data that's used to generate the graph on the right. So if you were to click an additional.
Sorry, are you by any chance using the crosstalk package?
I'm not in this one.
Okay.
Yeah, so you just kind of, you can, I think all of the kind of observers and other functions that I use for this are all kind of built in RShiny functions. And then kind of beyond that, in addition to these two packages, you can also integrate widgets kind of to further make this more interactive. So you can add buttons and checkboxes to kind of further change these graphs and have them respond to additional points of input. So in this example, there's a checkbox on the bottom that's like hide or show like the mean line where it's like hiding and showing the average for the value. You can also clear them with a button. And so these all kind of lend themselves very nicely to interactive and kind of constant input from the user. And so here's kind of some ways that you can use this and like in an air quality context. So it allows you to compare multiple counties in a really nice and seamless way. So on the top, you can see an example for vegetation. So essentially greenness across two counties in the Chicagoland area. So in the middle, you can see Cook County, which is where the city of Chicago is. And then on the bottom right is Pulaski County, which is a relatively rural county in Indiana. And you see how like the greenness changes over the years, because if you click both of these counties and you can see them kind of generate on the plot. And as you'd expect, a county that has a lot of developed land, like Cook County does, is going to have lower levels of greenness because there's less green space. Whereas Pulaski County, which is more rural, is going to have higher peaks. And then you can see the seasonality of the trends, how the greenness rises in the summer, in the spring, falls in the winter, and repeats every year. You can also do this with multiple variables. So I'd spoken about how that was a kind of big change from our phase one, was this addition of being able to compare variables. And these are kind of measured on different scales. So you're not going to be able to directly like compare greenness, for example, to BRF, which is essentially albedo or reflectance. But you can kind of compare trends and look for kind of seasonal spikes in different variables and how these might relate to one another. And it's a really good way to visualize trends over time with these two packages kind of in conjunction. And then another advantage of Leaflet when you're kind of doing this in RShiny is you can identify local patterns with these interactive maps. So, Plotly imports crosstalk. Just saw that message. Awesome. So the data that we have is at a 1 kilometer resolution. And so there's a lot more, like, there's a lot of data here that's like hard to analyze for any one person, but it's easy if you have a specific area of interest to kind of zoom in on that area and see what's going on. So here's an example looking at greenness in the area around the University of Chicago. That's kind of enabled by the interactivity of Leaflet. So you can see on the left side, there's kind of a lower levels of greenness where there's an expressway, which makes sense. There are higher levels of greenness to the right of that, where there are parks and the main quad. And so you can see kind of within a neighborhood of interest, how these things might be impacting the environment. And seeing as greenness is kind of one of the large drivers of air quality, how this might kind of impact the overall environmental kind of status in an area. Then you can do the same to look at kind of trends in aerosol optical depth, which is that proxy for PM 2.5 that Marinia had spoken about earlier. So if you look at the map towards the middle of where the word Chicago is the loop, which is the downtown area of the city. And you can see how aerosol optical depth is higher there. But you can see the kind of big overall spike actually comes outside the city near where it says East Chicago to the bottom right of that. So that like red area on the like thing sticking out into the lake. And that shows kind of how this high resolution interactive map is really useful, because that spike is only a few kilometer grid pixels like in diameter. So it might be missed if you're looking at larger aggregations. But because you have this kind of high resolution interactive map, you can see that there's this high pollution spike here. And it turns out this is a highly industrial area. And it's likely that this is contributing to PM 2.5 levels outside of it, because you have this industrial production that's creating more aerosols in the atmosphere there, which are going to then go elsewhere because of weather patterns and other things. And so that kind of also validates the expanding study area from just the city to a wider area, because it counterintuitively allows you to look at more interesting local trends, because you would have missed a larger trend that's happening at a wider scale. You might not have, if you hadn't known about that, you would probably not be able to tell why air quality in a nearby area of Chicago might be worse, or a possible influence for that. So then looking at this kind of in comparison to existing tools and getting at kind of one of the main goals of the dashboard, we had wanted to kind of provide a single platform for visualizing all of these different variables, all these different inputs, and also having them downloadable. And so a lot of platforms have them either visualizable, either downloadable. They don't have both, or they only have this for like one kind of set of data. And so we kind of wanted to streamline the process and make it more useful for policymakers. And so I'll do a quick demo of the dashboard now and just kind of how this looks in practice. Can you all see this? Awesome. So this is kind of what the dashboard looks like. So here's the like Leaflet Plotly integration that I've spoken about. And so if you, it kind of defaults to PM 2.5. And so if you want to see like the mean PM 2.5 over time, you can, but then you can also look at Cook County, which is where Chicago is, and see how, okay, Cook County over time seems to be above the average, less so recently, but overall, that's what the trend seems to be. Then you can hide the mean and compare a couple of counties. Say you want to look at Cook County in comparison to Walworth County, Wisconsin, which seems to be a pretty rural county, knowing nothing about Walworth County. And so it makes sense that the pollution, the PM 2.5 in Cook County is going to be higher than in Walworth County. You can also add additional variables here. So if you wanted to add PM 10, you could see that Cook County's PM 10 also seems to be higher than Walworth County's. And then over time, that PM 2.5 and PM 10 generally seem to track in the same direction. So you have this spike in July of 2015 with everything. You have these lower points that seem to be like relatively low here. So not an exact like one-to-one relationship, but definitely there's a relationship there. And then each of the variables has an individual page. So this is what it'll look like for NDVI, which is that greenness metric. So you have this kind of overall view. You can zoom in to the city of Chicago and then kind of look at local trends here. So this is that same snapshot I had shown where you have the expressway And then you also have like green parks, and you can kind of see the difference. And then additionally, for PM 2.5, this is just a rough like IDW interpolation. So the interpolation method that Marinia had spoken about for PM 2.5 from the sensors. And this kind of gets at the issue with making a surface from very few sensors, because these are the only PM 2.5 sensors available in the study area. And you can see that the entire like eastern section here has like one sensor across all of Indiana for these 6 counties, which means that your reading in the far southeastern county is pretty much only being influenced by a sensor 100 miles away, which makes it of pretty limited use. And then in addition to these variable pages, you also have all the data downloadable in a few different forms. And then just wrapping up with the last few slides. As Marinia was saying, we're kind of transforming this all into a toolkit, which will be the minimum of what we make public. So it'll be kind of an introduction to how to get the data into a form where this can be done. So it'll be introducing different spatial analysis concepts, and like each chapter will have a different focus. So we'll have like one on raster data, one on vector data, one on interpolations, and kind of how to do all of the individual processes that lead into making the dashboard. And this will all be done through Bookdown, which is like an R Markdown book creation platform. And then kind of next steps with the dashboard, finalizing a version for either public use or just a final version for city use, continuing to work with the city to make it fit their needs, integrating the training resources into it so that all information is available, and then updating it to include recent data because the dashboard does stop at 2018 at the moment. And so kind of main takeaways from this are that RShiny is super valuable for helping you visualize air quality indicators and using kind of other interactive packages in R to do so. It's cross-platform, it's easily accessible, and it allows people who might not necessarily be data scientists, might not necessarily be experts on environmental data, have easy access to stay informed about air quality in their community. The fact that it's open source means that it can be easily adapted to the needs of whoever wants, whoever's needs possible. And then finally, having the combination of high resolution data with interactive visualizations allows you to detect trends that you might otherwise have missed. Yeah, that is just about it.
Wonderful. Thank you so much. Let me see, go back to gallery so we can see everybody. Okay, we'll take questions. First of all, yeah, applause. Thank you so much for the presentations. Yeah, I open up to the floor if anybody has questions. I have one right off the bat. What are Chicago colors? I'm not familiar with that.
If the city doesn't have a flag, that there are some.
Oh, it's like a flag thing. Okay, I didn't know like where the theme came from because you mentioned there's more Chicago colors. I didn't know what that meant.
There's a flag. It's like light blue, 2 light blue stripes and a white stripe with a couple red stars. So like light blue, white, and then each of your highlights is red. So with public health dashboards, you have to be careful on how you use red. So here it's just kind of like a feature selection tool.
Oh, I see. Okay.
Hear that? I think a couple of folks were talking about Leaflet and how that is more effective or less effective. So it's interesting because like in cross-sectional work, I'll use Tmap as my standard for just making like one-off maps. But in this case, it didn't have the same speed. So I don't know, Isaac, do you want to talk about that process of like figuring out which was the most optimal?
I completely agree. Like I also use Tmap like whenever I'm doing pretty much anything but RShiny. But for RShiny, Leaflet's like because Leaflet defaults to interactive maps. And so it doesn't have, like Tmap winds up having some weird glitches if you're changing interactive maps a lot. Whereas Leaflet kind of, that's their default. So it all works out pretty well.
And so if somebody were interested in starting, I guess like first getting into this, like if you had recommendations on resources for somebody to start learning either these packages or spatial data analysis in general? Do you have suggested set of resources online, preferably free, that you know of?
Yeah, so there's probably a couple different ones. So one of my favorites for geocomputation or for spatial analysis is Geocomputation by Lovelace et al. And that's a free online text. That's a pretty intensive overview though. So I use that in my like intermediate or advanced classes sometimes because you have to be, I feel like you have to feel pretty comfortable with the R space for that and also come in kind of knowing what you want to do. I think that's another big challenge is like, for example, if you don't know what a spatial join is, like I had some students before I taught them what a spatial join is work on a project and they couldn't, and they're like, all right, so we have these zip codes and we have this other data set that I need to match to that. And they spent hours and hours like manually checking Google Map to kind of figure out where each one of these plotted.
Oh, no.
Where if you had the same data sets, it's like a 2-second operation in R or other languages, but you have to know to look for spatial join when you're Googling something, right? So knowing, Lena, that's funny. Like you have to know there's a little bit of a jargon challenge sometimes, especially with any discipline, but the geocomputation text is pretty good. Also, I feel like for Leaflet, I know I started off just on the Leaflet tutorials that are on the Leaflet website, and there's also a nice, I think there's like one using Leaflet in R tutorial set. I haven't found more than one, but Isaac, because you had to figure this out pretty recently. So anything there?
I think it was just the Leaflet website. Yeah.
And then our group for a different project just released this toolkit. It's like an application driven thing. So if you're looking for a very gentle intro to how to geocode resources or pull census data from R or do things like buffer analyses, like even though it's about opioids, like you could still kind of, it's a very gentle onboarding that kind of talks more about like what the concepts are, why you might want to do something and that sort of thing. Yeah, I think and there's a lot of resources out there, but and let's see, I think the data carpentry workshop also has a really nice intro to kind of spatial analysis in R that will definitely be more focused on raster data though. So I don't feel like I know enough people. So a lot of the folks or like the students I've worked with who've gotten comfortable working with raster data, it seems like the geocomputation text by Lovelace was the most effective teaching tool, but that might be a sampling bias because I don't know enough students who've taken the data carpentry series, if that makes sense. But Jakub Nowosad, he's a Polish geoscientist, and he was the one who I believe was responsible for a lot of the raster training materials. So if you're interested in that, look that name up. It's interesting because a lot of times in spatial stuff, it's more by like you find a person that you understand their tutorial style, or you think that they do a good job, and it's more about like hunting down stuff like that. Like in the Python world, one of my colleagues, Dani Arriba-Spell, if anyone tells me they want to learn spatial analysis in Python, I'll just direct them to his website and like look through all the stuff there because he has a bunch of tutorials. So I feel like there's still there's a lot of code out there, but I think the tutorials, there's still a lot of it is still in process of like what are the best ways to teach and that sort of thing.
Makes a lot of sense. Thank you. These are really great resources. I'm going to add them to my list. Are there other questions from the participants in the meeting? Is there anybody who's creating similar interactive dashboards or doing spatial data analyses in the group? I'm starting to work. Oh, I was just wondering if anybody in the room was starting to work either with spatial data, geospatial data, or starting to use some of these packages for their own work, and if they had feedback on what they like or don't like.
No, I really like it. So just a little bit about myself. My office at the Bureau of Labor Statistics, we just put out a a new data series called State Level Labor Productivity. So our office was mostly known for the national measure, but now we have it down at the state level. So we're working more with maps and different things like that. And I've also been using a lot of mapping packages in R. And I could definitely attest that Leaflet is one of the most beautiful packages I've seen. And I really like how the presenters had shown Leaflet and Plotly, because I was always trying to figure out to do something like that, but I was never able to get the plots to be together like that. So thank you.
Like that interaction is so like on the spatial side of things, like we'll get really spoiled and like used to different software that does it for us already. And then like for me, I got used to that interaction. So there's an official term for it, brushing and linking. So I got used to being able to brush and link across multiple different things. So then when that wasn't available in output, it'd be really frustrating. It's one of the things that propelled my divorce from Python, where I was really frustrated with how Matplotlib was rasterizing a lot of their images in the last step. And it kind of like, you have to add all this, you have to do this massive uphill battle to work with event listeners to get the interaction to work the way that you need to, right? Whereas R, I feel like it's just the interaction is just so much more seamless and really exciting. So yeah.
That was going to be one of my questions, kind of where is the state of things in the Python world for spatial data analysis? I guess you kind of answered it, but I didn't know if you had other thoughts.
Well, so my one dig is only, I guess, at the interactive visual piece. There is a really active, a small but active spatial analysis community. So PySal, that stands for Python Spatial Analysis Library. That's basically the library that you're going to want to go to for data processing. So there's pandas, but then GeoPandas is kind of the spatial version of that. GeoPandas is to Python what SF is to R, right? So if you're interested in Python, extending pandas to GeoPandas, and then starting to work with the PySal library is pretty nice. And so the guy I mentioned earlier, Danny Rebespel, he is very passionate, but then also more patient than I am, and has been doing a lot of upgrades to kind of to beef up the interactive visualizations and that sort of thing on the side of Python. So I think that's pretty phenomenal. But still, with R Shiny, like there's no easy match to what, like we couldn't have done what we did in Python. We would have had to create a separate, we would have had to use Python differently and like set up a system with Flask and like create basically a whole piecemeal kind of full stack architecture to pull it off. Whereas R Shiny creates that, yeah, it's a lot more work. Yeah, and I think too, like what was interesting here was that I don't think when we started with R Shiny, because we know that R Shiny can be slow sometimes, I don't think we anticipated that it would have actually been so responsive and fast. But the trick is you have to have really clean standardized data. And if you optimize it from that end, then yeah, and if you have really patient students, like I'll get really frustrated with something quickly. And so like, I think Isaac, there was that summer, I was like, all right, figure this out, right? You need like time and patience to kind of work through that, which is exciting.
All right. Well, thank you so much. And I'll, if anybody has any other questions about upcoming R-Ladies events or R-Ladies Baltimore in general, please feel free to reach out either by email or on Slack or by Twitter. We welcome your feedback on today's meetup. And we'll hopefully have the video up on YouTube soon. I'm about usually a week behind in that, but hopefully soon enough. All right, another round of applause for the presenters today. Thank you so much, Mariana, Isaac.
Thank you guys. Thank you.
All
And
right.
we'll share the slides too, so that can get squared away.
Perfect.
Cool.
All right, take care, everyone.